Ever find yourself, looking at an app and just thinking, wow, this thing is fast, even when it's doing like a million things at once?
Yeah, absolutely. And then the opposite happens too, right?
Oh, definitely. You click something simple like a download, and suddenly the whole application just freezes,
Hmm.
staring at that spinning wheel of death.
The dreaded spinner. Yep.
Well, today we're going to dig into something that often makes the difference between those two experiences. We're doing a deep dive into multi-threading in Java.
Mm-hmm. It's a core concept.
Exactly. We've gathered a bunch of sources, sort of a beginner's guide plus some deeper stuff to really unpack what it is, why it's so powerful, and what you really need to know. We're aiming for those, those aha moments.
Right. So at its heart, multi-threading in Java is, well, it's a feature that lets your program do multiple things kind of simultaneously.
Okay, simultaneously, how does that work?
Well, each task is handled by a separate thread. And a thread is like the smallest possible unit of execution your program can have. Think of it as a lightweight process.
Lightweight process. Got it.
Yeah, and they can run in parallel, which is great for today's multi-core processors.
One of the sources used a really good analogy, didn't it? The kitchen one.
Oh yeah, the kitchen analogy, it's pretty helpful. Imagine your program is a kitchen,
Okay.
and threads are like workers in that kitchen.
Yeah.
So one worker might be chopping vegetables. That's one thread. Another is boiling water. Another thread, maybe a third, is prepping a sauce.
Right. All happening at the same time in the same kitchen.
Exactly. They're working independently, more or less, but, and this is key, they're all sharing the same kitchen space, the same counters, the same pantry.
That shared space being the program's memory.
Precisely. They share the same memory space. That lets them work together really efficiently on related tasks. But it also means you need careful coordination. Otherwise, they might bump into each other, metaphorically speaking.
Makes sense. And Java itself helps with this.
Oh, absolutely. Java has built-in support right from the start. You've got the thread class, the runnable interface, and then a whole bunch of really useful tools in the java.util.concurrent package.
That concur package comes up a lot.
It's super important for modern Java concurrency. And, it's worth quickly mentioning, this isn't the same as multiprocessing.
Right. Good distinction.
Multiprocessing means separate programs, separate memory, easier to keep things isolated maybe, but talking between them is slower. Multi-threading is all within one program, sharing memory,
Yeah.
faster communication potentially, but yeah, needs that careful management we talked about.
Okay, so that's the what. Let's pivot a bit to the why. Why go through the trouble? When does multi-threading become, like, essential?
Yeah, good question. It really boils down to a few key things: performance, responsiveness, and just using resources efficiently.
Performance seems like the obvious one. Using all those CPU cores we have now.
Exactly. That's a huge driver. Think about it. A typical program might just use one core, leaving the others idle. That's wasted power. Multi-threading lets you split up heavy tasks, think image processing, big data calculations, that sort of thing, across multiple cores. So the whole job gets done much, much faster. You're actually using the hardware you paid for.
Okay, so raw speed is one thing.
Yeah.
But you also mentioned responsiveness. That sounds more like the user experience side.
It totally is. And this is often just as important, maybe even more so for user-facing apps. Remember that freezing app scenario?
Yeah, the spinner.
Right. So imagine your app needs to download a big file or run a complex query in the background. In a single-threaded app, the user interface, the part you click on, would just lock up solid until that task is done.
Ugh, yeah, frustrating.
Totally. With multi-threading, you can run that background task on a separate thread. The main thread, the one handling your clicks and scrolls, stays completely free and responsive. It feels fluid.
So it keeps the UI alive while work happens behind the scenes. That makes a huge difference in how an app feels.
A massive difference. And it ties into that resource utilization point, too.
Yes.
Because threads are, as we said, lightweight, they share memory, so creating a new thread takes way less memory and fewer system resources than starting a whole new separate process.
Ah, okay, so you can handle more things happening at once without bogging down the system as much.
Precisely. This leads directly to better task parallelism.
Mm.
Think about a web server. It needs to handle maybe hundreds or thousands of user requests coming in at the same time.
Right.
Multi-threading is perfect for that. Each incoming request can be handled by its own thread. The server can manage all these concurrent requests efficiently.
And that allows for asynchronous processing too, right? Like
Yeah.
kicking off a task and not waiting for it to finish immediately.
Exactly. Things like reading from a database, fetching data over the network, these can take time. Multithreading lets you start those operations on a background thread and let your main program continue doing other things. It doesn't have to just sit there waiting.
So for you listening, if you're building apps, especially anything handling multiple users, real-time data, or potentially long background tasks, getting a handle on multi-threading is pretty crucial for making things feel fast and not broken.
Absolutely. It's about building resilient, scalable systems.
Okay, let's dig a bit deeper into those advantages. We mentioned faster execution.
Right, especially on multi-core processors. If you have a task that can be broken down, like storing a huge list of data, you can split the list, give each chunk to a different thread running on a different core, and then combine the results. The total time can be dramatically reduced.
And the user experience benefit the no-freezing UI thing that's worth hammering home, isn't it?
Definitely. It's about continuous interaction. The user never feels locked out, even if the application is doing heavy lifting in the background. That perceived performance is huge.
And the resource sharing aspect. You said shared memory means faster communication.
Yeah, compared to interprocess communication, or IPC, where separate processes have to use more complex, slower mechanisms to share data because they don't share memory. Threads within the same process can access the same objects directly, which is much faster and more efficient. Needs coordination, of course, but it's faster.
That sounds like it helps with scalability, too.
It does. As hardware gets better, more cores become available. A well-designed, multi-threaded application can often take advantage of those extra cores without major code changes. It scales better with the hardware.
Does it also help with how you structure the code, like modularity?
That's a great point. It often encourages you to break down complex problems into smaller, more independent tasks. Each task can potentially run in its own thread. For example, you might have one thread dedicated just to logging, another for performing calculations, another for handling network communication.
So it can lead to cleaner, easier to manage code.
Potentially, yes. Easier to design, test, and maintain these smaller, focused units. So yeah, for the listener, the big takeaway on advantages is building apps that just feel seamless and efficient, even when they're doing complicated stuff.
Okay, so we know what it is and why it's useful. How does this actually work under the hood? What's Java doing?
Right, the internals. The key player here is the Java Virtual Machine, the JVM. It's the one managing everything.
How does it manage the threads?
Well, you create threads, like we said, usually by extending the thread class or, more commonly, implementing the runnable interface. Once a thread is created, the JVM takes over scheduling it.
Scheduling.
Yeah, deciding when each thread gets to run on the CPU. Threads go through different states, like new when created, runnable when ready to run, running when actually on the CPU, waiting if it's blocked, and finally terminated.
And the JVM's thread scheduler is the thing deciding which runnable thread gets to be running.
Exactly. It's constantly juggling these threads, allocating CPU time. It might use preemption interrupting a running thread to let another run, or time slicing, giving each thread a small slice of time. The specifics can vary, but the scheduler's job is crucial.
And this juggling leads to that context switching concept, right?
Yes, context switching is fundamental. Since you usually have more threads than CPU cores, the CPU has to rapidly switch between them.
Creating the illusion they're all running at once.
Precisely. To do this, when the CPU switches from thread A to thread B, it has to save thread A's current state, its registers, program counter, basically where it was and what it was doing. Then it loads thread B's saved state so it can pick up where it left off.
That sounds like it has some overhead.
It definitely does. Each switch takes a tiny amount of time, but if you're switching constantly between many threads, that overhead can add up and actually slow things down. It's a trade-off.
And all this happens while they're sharing that same memory space we talked about.
Right. They can all access the same objects, the same variables. That's great for communication, but it's also where the danger lies. It's why synchronization is so critical. You need mechanisms to make sure threads don't interfere with each other when accessing shared data.
Okay, so the JVM scheduler manages the time, context switching creates the illusion of parallelism, and shared memory requires coordination.
You got it. And Java provides tools for that coordination in the java.util.concurrent package we mentioned earlier. Things like thread pools, executors, locks, semaphores, tools to manage threads efficiently and safely.
Thread pools sound important. What do they do?
Instead of creating a brand new thread for every single task, which is expensive, a thread pool maintains a collection of ready-made worker threads. When a task comes in, it gets assigned to an available thread from the pool. When the task is done, the thread goes back to the pool, ready for the next task.
Ah, so it reuses threads,
Ugh.
reduces that creation destruction overhead.
Exactly. Much more efficient, especially if you have lots of short-lived tasks. It helps manage resources better.
There was another analogy for how this all works internally, right? The juggler.
Yeah, the juggler. Think of the JVM as a juggler, and the threads are the balls it's keeping in the air. The JVM has to give each ball thread enough attention, CPU time, to keep it flying, but it also needs incredible coordination to make sure the balls don't collide and everything comes crashing down.
It's a good visual, captures the complexity. It sounds powerful, but also fragile.
That's a perfect way to put it. Powerful, but you have to be careful. Which brings us neatly to the flip side, the challenges and limitations.
Right, it can't all be sunshine and rainbows. What are the big pitfalls developers run into?
Oh, there are definitely pitfalls. The biggest one is probably just the overall complexity it adds. Writing correct multi-threaded code is significantly harder than single-threaded code.
Harder how? What kind of bugs show up?
Well, the classic ones are race conditions and deadlocks.
Okay, break those down. Race conditions.
A race condition happens when the outcome of your program depends on the unpredictable sequence or timing of threads accessing shared data. Imagine two threads trying to update the same counter at the same time. If they both read the value, then both increment it, then both write it back, you might end up incrementing it only once instead of twice, because one overwrites the other's work. The result depends on who wins the race.
Ugh. Sounds subtle and hard to find.
They can be incredibly subtle and intermittent. And then there's deadlock.
Deadlock. That sounds bad.
It is. Deadlock is when two or more threads are blocked forever, each waiting for a resource that the other thread holds. Like, thread A has lock 1 and needs lock 2, while thread B has lock 2 and needs lock 1. Neither can proceed. The program just freezes solid.
Wow. Okay. I can see how debugging that would be a nightmare. You mentioned chasing one for 3 days.
Yep. Production system. Not fun. These kinds of bugs often only appear under specific timing conditions or high load, making them really hard to reproduce reliably during testing or debugging.
So complexity and tricky bugs. What else? You mentioned overhead before.
Right. Creating threads, managing them, context switching it all consumes CPU time and memory. For very small, quick tasks, the overhead of setting up and managing a thread can actually take longer than just doing the task sequentially in the first place.
So using threads isn't always faster.
Not always. You need to profile and measure. And related to overhead is resource contention.
Contention, like fighting over things.
Exactly. If multiple threads are constantly trying to access the same shared resource, like a database connection pool, or even just shared memory that requires locking less, they can end up waiting for each other, effectively serializing the work and slowing things down. Too much competition can bottleneck the system.
And is there a limit to how many threads are useful? Can you have too many?
Absolutely. While multithreading helps scalability up to a point, adding more and more threads doesn't infinitely improve performance. Eventually, the overhead of managing all those threads and the increased contention starts to outweigh the benefits of parallelism. The system gets overwhelmed, context switching goes through the roof, and performance actually degrades.
Okay, so it's a powerful tool, but definitely one that requires care and understanding. So for someone listening, maybe newer to this, what are the key takeaways? The practical steps to get started without shooting yourself in the foot?
Good question. The sources offer some solid advice here. First, start simple. Don't try to build a massively concurrent system right away.
Makes sense.
Yeah, maybe just run a simple task in the background, like updating a progress bar while something else loads. Get comfortable with just creating and starting threads, maybe using Runnable.
Okay, basic execution first. Then what?
Then you have to learn about synchronization. This is non-negotiable. Understand synchronized blocks and methods, understand locks, reentrant lock, etc. Learn how to protect your shared data from those race conditions. It's fundamental.
Protect the shared state.
Got it. And then leverage the high-level tools Java gives you. Seriously, explore the java.util.concurrent package, especially the executor service framework and thread pools.
Why are they so important?
Because they abstract away a lot of the low-level complexity of manually creating, managing, and scheduling threads. They handle thread lifecycle, reuse threads efficiently via pools, and often lead to cleaner, more robust, and better performing code. Don't reinvent the wheel if you don't have to.
So use the built-in frameworks when possible. What about testing?
Test, test, and test again. And not just simple functional tests. Because concurrent bugs are often timing dependent, you need to test under various conditions, different loads, maybe even introduce artificial delays sometimes. Stress testing is crucial to try and provoke those elusive race conditions or deadlocks.
Be thorough because the bugs are sneaky.
Exactly. And related to that, avoid overthreading. Remember that more threads isn't always better.
Right, the performance degradation point.
Yeah. Use thread pools to manage the number of active threads effectively. Size them appropriately for your workload and hardware. Don't just spawn threads wildly.
Be mindful of the resources. What about knowing when to use it?
Critical point. Understand the use cases. Multi-threading shines for I/O-bound tasks, like network requests or disk reads writes, where threads can wait without consuming CPU, for tasks that can be genuinely parallelized across CPU cores, heavy computation, and for keeping UIs responsive.
And when is it overkill?
For simple, inherently sequential tasks, or very short tasks where the overhead outweighs the benefit, sometimes a straightforward single-threaded approach is simpler, safer, and perfectly adequate. Don't add complexity for complexity's sake.
Makes sense. Choose the right tool for the job. Anything else?
The last big one is really study and practice writing thread-safe code. Learn the patterns and techniques to design your classes and methods so they behave correctly even when accessed by multiple threads concurrently. Think about immutability, proper locking, using concurrent data structures. Design for concurrency from the start if you know you'll need it.
Okay, that's a lot to keep in mind, but really practical advice.
It's a journey, for
Yeah.
sure.
So just to recap, we've kind of journeyed from the basic idea of threads running concurrently, explored why that's so vital for performance and responsiveness, peeked under the hood at how the JVM juggles it all with context switching and schedulers, and then really dug into the complexities, the deadlocks, the race conditions, and how to approach it practically as a developer.
Yeah, it's a fascinating area. It really changes how you think about program execution.
It really does. And what's maybe most compelling, as you said earlier, is thinking about how mastering this careful dance of threads unlocks this entirely new level of, well, computational power and user experience. It really transforms what software can actually do.
And the core ideas, concurrency, parallelism, managing shared resources, they pop up everywhere in computing, not just in Java. It's a fundamental concept for building efficient modern systems.
So here's a final thought for you listening. Think about an application you use every day, maybe one that feels particularly smooth or handles a lot of complexity well. Could be a game, a creative tool, even just your web browser with all those tabs. How might multi-threading be working, behind the curtain, choreographing all those little tasks to make it feel so seamless? And now that you know a bit more about the juggling act involved, what might you look for or appreciate differently in the software you use or even build?